All right, in this video, we're still talking about the applications of the exponential growth and decay model. We talked about how that this is the continuous compounding model, where A is the amount it grows to, or decays. If it's a decay, you'll have a negative exponent. So we can do decay as well. But the example we're going to do, example 4, is a growth. We're putting some money in the bank at a certain rate over some time and having it grow to an amount. So this problem says, say we deposit $500 in the bank. That's our p-value. E is that E that's on our calculator, about 2.72. It says how much money will be in the bank after 2 years. So we know T is 2. If the bank compounds continuously, that's this formula is continuously at 5%. So 5% has to be changed to a decimal, 0.05. So we got 2 for time and 0.05 for the rate. So how much money is that? So we can put that in our calculator, and please do. 500 E to the X makes the up arrow. That makes it 0.05 times 2 like that. Hit the equals and see if you got the same thing I have here. 552.59 cents. So that's how much $500 grows to after 2 years at 5%, compounded continuously. So when will this amount double? We did a doubling problem a little bit ago, but that's a common problem. We want to hit that again. So how long does it take this money to double? It got up to $552. How long before it gets up to $1,000? So let's look at that. How long would it take $500 to become $1,000 at 5%? And I don't know how long. So that would be that equation, solving for T. The first thing we would do is divide by 500 on each side to get that to cancel. And look what we have, 2. Doubling times whatever amount this is. Sometimes they don't tell you what that amount is because it really doesn't matter. If it's $500, $600, $2 million. When we double it over here and then divide by that, it should give you a 2 regardless. So doubling time, you get 2 equals the E raised to the rate times time. And the way we solve that problem, we've seen in earlier videos, to get this to come down, we have to take the logarithm. The logarithm rules make our exponents into multipliers. So you have to introduce the logarithm application there. By taking the logarithm, that now is a multiplier in front of ln E. Multiplied onto that are all on the level there, you know. ln of E is always 1. So this times 1 is just this. Then we divide by the 0.05, and then that gives us our T value. Type this in your calculator, see what you get. Okay, you should be getting about 13.86. That's how many years it takes, really any amount of money to double. Like I said, it doesn't really matter. This $500 is kind of arbitrary. It could be any amount. So any amount of money at 5% should double, compounded continuously, in about 14 years. So you might wonder, well, what if it's at 6% or 7%? You could play around with this formula because the shortcut is it's just ln of 2 divided by the rate. When you're doubling, ln of 2. If it were tripling, it'd be ln of 3. If it's a half-life, ln of a half. Whatever the increment of time is, it's ln of that divided by the rate. All right, so you could work with that formula. So this next thing comes up in banking, and it's also just a really cool thing to know. It's called the Rule of 70, and it's an application of this or a shortcut to this, kind of our shortcut we're using here. Again, it's called the Rule of 70. And it says, one useful bit of information from banking, this Rule of 70, if you want to know approximately how long it takes your money to double when it's being compounded continuously, you divide 70 by the rate of interest without the percent sign. So notice this, if we do 70 divided by the percent, 5%, that is 14. Comes out to be 14. And it's just true for any amount. 70, now why would that work? Let's all check. What is ln of 2? Doubling time, we were doing ln of 2. And let me see, what is that? ln of 2 on your calculator is 0.69314. So where's this 70 coming from? And they say don't do that as 0.05. If you do it as 5%, so they've moved that decimal 2 places to make it just the regular amount, so people don't want to have to deal with that decimal point. You know, normally to make easier math, move it over. Then they had to move this one over too. So look, 69.3, that's almost 70. So it comes out to be pretty daggone close. It's not an exact value, but you know, because you get 14 instead of 13.86, but it's a good estimate. So really, the rule of 70 says just take 70 divided by the interest rate. So what if you're getting a better interest rate on your 401k or your retirement? Say you're getting a 7% return. So 70 divided by 7%, your money doubles in 10 years, right? What if you'd get 10% return? 70 divided by 10%, your money would double in 7 years. So you can kind of see how that is, you know, if you're hoping for better interest rates in your savings, that could really speed up retirement for you. All right, so again, rule of 70. Next page. Okay, the next thing we're going to look at is other examples of quick growth. So what else grows quickly that you can think of? Quick growth things. And something that comes to my mind is the use of smartphones. Do you know smartphones were just invented in the year 2007? I mean, wow. Here's an example of a quick growth. Kind of, you can find some charts online, and I've cited my source there if you want to look at it. But notice that it's a curve that shows, and you all know this was true when smartphones came out. People started to get them, and then like, boom, seemed like everybody had a smartphone. So it's a quick growth curve. That's an exponential growth curve. And that's what we do in math. We try to model, like, is this thing linear? A linear growth is kind of a solid one slope fits all. There's a consistent slope all the way, so we can find the slope m of a line. So we have linear growth. We have our parabola growth. We could have a parabola shape. And then what we're seeing here is an exponential shape. So exponential growth. And can you kind of see your example here that it fits that curve? It grows along what we would consider an exponential curve. And then there's other types of curves, other things that we study. But we try to model something like, what model does this data seem to fit into that makes the most sense? So we learn these different models as we go through college algebra, and then we would use them to try to make predictions and gather data. And they do more of that probably in statistics class. They would gather the data and then make predictions. But it stems from what we're learning here in the algebra class. Another thing would be any type of population. Population growth can be a quick growth with our people or with animals. For example, mice is a good example of quick growth. Mice mate every 6 to 10 weeks of age, Then 5 to 6 babies are born after 3 weeks. So it's a very, very quick turnaround. Then 6 to 10 weeks later, they all mate and continue this pattern again. In 6 months, that would make 128 mice. So quick growth. COVID-19 was quick growth. The estimates of the basic reproduction number have it somewhere between 1.5 and 4. This article assumes a figure somewhere in the middle with 2.5 infectious contacts per infectious individual. And I have a source there if you want to look at that more detail. All right, so now we're going to move on to example 5. And we're going to talk about decay. So we've talked about growth models, but we've yet to talk about some of the decay models. Now, you've seen decay in an earlier video because we did some half-life examples, but here's where it shows up in this section as well. So if we have our fancier formula, P sub t equals P sub 0 times e to the negative k t. If this is negative, if you have a negative rate, then it's going to be decaying. This will be less than it started. All right, an example of that, you can look this up as well. There's a source here if you use the document. And we talk about the Mythbusters did this. There's a myth of the 12-year-old McDonald's burger that just won't rot. But this is true for like a lot of food. It just won't rot. What's in our food that makes it, have the staying power? So things should rot. Living things rot. But long story short, it just basically was not rotting after a long time. And so we were looking at, normally if something like, I don't know, if you put an apple out in a compost pile, it should rot away to half of itself after a certain amount of time. You'd expect some rotting to go on. So what is the half-life of this burger? And if you look, if you kind of Google, like, what is the decay rate of burger or anything like that, it depends on a lot of factors. So I couldn't get a real solid statistic, you know, that always works. It depends on the humidity and lots of things. So we'll just pretend we found the decay rate is 0.03% per year. So we'll plug that in for K, change it to a decimal, of course. So we'll be plugging in that as a decimal, and it will be negative because it's a decay rate. So whatever we started out with, and it doesn't really matter if it's a 1/4 pounder or a 1/2 pounder or whatever. Whatever it is, piece of 0, when it becomes half a piece of 0, whatever it is, let's look at that. We know the first thing we do is divide that number out anyway. So it always reduces out to half, if you're doing a half-life, equals ERT. So that's our problem we'd be solving. And as you've seen in all the previous problems, then we take the ln to solve these over and over again. You see that. So when we take the ln of each side, we have ln of a half. On this side, the exponent comes down, as that's what it does with the logarithm rules. ln of e is always 1. Divide by what's with your variable on each side. And there is your t value. Solving for time, type that in your calculator, you know, check that out. 2,310 years and some decimal amount. And again, I don't say that that's absolutely true answer. It's just something to give us an idea of how we could find this out if you knew the decay rate. That would be your steps. So what if you did a 4th life? So I'd like you to pause the video and try that. Instead of a half-life, now do a 4th life with that same percentage. How long till 1/4 life is left? So our shortcut is you take the ln, instead of a half, it'll be the ln of 4th divided by the rate. How many zeros did I have? 3 zeros, and it was negative. So the shortcut for all of these, if it's a doubling time, we saw ln of 2 divided by the rate. If it's a tripling, ln of 3 divided by the rate. A half-life, ln of a half divided by the rate. So a 4th life would be ln of a 4th divided by the rate. So check that out. Type that on your calculator. I will as well. And let's see how long it takes the 4th of it to be. So ln of a 4th divided by negative 0.0003 would be 4620.9 something around that, depending on what they said to round to. All right, last application. I think I'll come in on the next video and we're going to talk about carbon dating and how that formula can help us find how old something is based on the carbon found in a substance. So that up in the next video.